coats. All right. I put your grades up on what's today? Today is Friday. I put them up on Wednesday. Unfortunately, I'm not going to give your test back today. You'll get it back. You know we have fall break. My wife just told me this morning that we're not meeting on Monday or Tuesday. So that was good news to me. I'm kind of glad for it. I need a break. Y'all do too? I need a break? Yeah. So I do want to just sort of clarify the numbers that I put up. I put up all of your exam grades and your class participation grades. I also put up what I expect your class participation to be. That's just sort of an estimate. I think it's probably a little bit of an underestimate. So if you're not quite up to 50, but you're almost to 50, then good chance that you'll get up there. So like if I estimated your class participation between 45 and 50, I suspect, come to class, make sure you get all the answers right that you can, that you'll get bumped on up there. So, um, but if you haven't been coming to class or you haven't been participating in the quizzes, then you're probably not going to max out that 50 points. But most of you will. I also put in those values to make an A, to make a B, C, and D. And those might look something like this, like 104, 80. So they were 24 points. So that's what, 56 and 32. What these numbers mean, these are just for example, these aren't anybody's numbers. What this means is that on the next two things that we have, given that estimated class participation grade and your extra credit that you've already gotten, these are the grades that you need to get on exam 4 and the final in order to get an A, B, C, or D. So for example, this student, it's not really possible for this student to get an A in the class. So this student should shoot for getting a B in the class, and they'll need an 80% on exam 4 and an 80% on the final exam. Now the final exam is actually 150 points, so they would actually need 80% of 150 in order to get a B in the class. So this student, I would recommend that they shoot for getting a B in the class. A C, they're probably pretty much locked in on a C. But that student cannot get an A in the class, okay? Because you're not going to be able to get 104. And so, for example, if your distribution was something like this, where you had a really high number out here, like if you had, I don't know, 120 out here in the D column, that means that you should really think about dropping the course, okay? But if that's going to be the case, come talk to me. If you're thinking about dropping the course, come see me, and we'll just make sure that everything's on the up and up and that it's really as bad as you think, okay? Y'all follow what those numbers mean? That were helpful for you? Sort of figure out where you are. Now, if you want to calculate your average, so far we've had 3 exams, so that's 300 points. We have the class participation. Right about now, your class participation, I think, do you remember what the maximum I put there? I think it was like 45. I think your class participation should be right around 35 or 40, if I'm not mistaken. Um, but if you use that estimated class participation, that's out of 50. You can just add up the 3 exams and your class participation and divide by 350. Okay? If you want to know your current average. I'll return those exams on Wednesday of next week, and I will likely put up the solutions this afternoon. I'll send you an email if that's the case. Probably I will put them up this afternoon. Well, let's move on to Chapter 7. We're going to see one more thing, or a couple of new things in calculus here. We'll do the vector product or the cross product, and then we'll also see we'll do volume integrals as well, which some of you may have seen, I think Calc 3, but don't worry, I'll give you what you need to know on this. It'll be okay. Vector calculus, the cross product. The cross product or the vector product. So this is in contrast to the dot product that we had before. Uh, the dot product was called the scalar product because the result of the dot product. Yes. No, this is 234. It's sort of the preface to, isn't it? Don't you have that? Oh, it's on the back of chapter 7? Oh, I'm sorry. Yeah, we're waiting off on this then. I'm sorry. Just skip chapter 7? No, we need chapter 7 for chapter 8. So let's Sorry about that. Okay, yes, chapter 7. So chapter 7 and chapter 8, they sort of go together. You can even think of chapter 7 as sort of a preamble. So on the next test, we're probably going to have 7 and 8 together. 9 will be a take-home test, and then we're going to do either chapter 10, which isn't in your book. Probably not going to do chapter 10, which was on oscillations. We're probably instead going to do optics, which Dr. Balaji really wanted to do optics, like geometrical optics. You'll find that it's pretty straightforward. It's really just sort of a few simple rules. Okay. Um, so 7, 8, 9, and optics on the next test. All right, so chapter 7 is on rotation. We're going to see everything that we've done up till this point. Kinematics, Newton's laws, angular, our momentum, energy, all that's going to come back. Actually, going to all come back in this chapter and chapter 8. So we're going to talk about the rotation of rigid bodies. A rigid body means that all parts of the body move at the same angular speed or angular velocity. And the parts do not move with respect to one another. So like if I'm a rigid body, that means that I can hold out my arms like this, and every part of me moves at the same angular speed. Now, not every part of me moves at the same linear speed, right? So if I'm spinning around like this, I have the tips of my fingers. Will they move faster or slower than, say, my elbow if I'm spinning around like this? My fingers move faster because they're a further distance from the axis of rotation, but they're still moving with the same angular speed. So anytime I have a rigid body, every part of it will move at the same angular speed. So an example of a rigid body, a spinning chair, I don't know, any sort of hard object that spins around. What's an example of a non-rigid body, however, where parts of the body can move with respect to one another? Okay, yeah, tetherball, yeah, if the rope is changing length, sure. But what's another non-rigid body? What's something that's not rigid? Right, like a steel bar is rigid. What's not rigid? Solids are rigid. What's not rigid? Liquids. All right. So yeah, so fluids, things that flow, are non-rigid bodies. Those of you in engineering, of course, you'll take multiple courses perhaps on fluid flow, and it can get pretty complicated. We don't address fluid flow at all in this class, but the engineering majors, you'll certainly see that again. Okay, the axis of rotation is just the axis about which a body rotates. We'll see in chapter 8 that this makes a big difference in how a body rotates. That a body might rotate very easily about one axis, but not very easily about another axis. And we'll get into that in chapter 8 where we're calculating the moments of inertia of bodies. So, for example, I can rotate my body in a lot of different ways. I can rotate about an axis like this, where I rotate about an axis that goes down through the middle of my head. That's like a ballerina, right? Or whatever. Ballerinas do all sorts of stuff. Uh, but I can also rotate about other axes, right? Y'all ready to watch? I'm going to rotate about this axis. You ready? Whoosh. I can rotate about this axis. Actually, I can't. But if I could, I would. And I can also rotate about this axis, right, through my hips. Those are really sort of our three big axes, our x, y, and our z axes, right? The y-axis, the x-axis, the z-axis. So you can rotate about any one of those axes or in between. So the same body can have different axes of rotation. uh, that will affect how the body rotates. This is just an aside. I saw this video the other day uh, about up-down dizzy. Have you ever heard of this? You should look on YouTube. The AAPT, the American Association of Physics Teachers, puts this out. Just search up-down dizzy. Because, if you spin around like this, you get dizzy. And it's because inside of your ears, you have these fluid-filled chambers. And if you spin around, that fluid keeps moving after you stop spinning. and it makes you feel dizzy because it tells you, oh, you're still moving when you're not really moving, and your brain just sort of has difficulty dealing with that. But you actually have three axes of chambers. You have a chamber that goes like this, a chamber that goes like this, and a chamber that goes like this. That helps you orient your body and how you're moving. So when you spin around, that's like a side to side dizzy, and it feels like you're still sort of spinning and moving side to side. But if you rotate your head like this and then spin around, it 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 mixes up those chambers, and it actually causes another chamber to cause the fluid to move, and it's up down dizzy. I'm not going to do it here because I'd fall on the floor. You can't stop from falling on the floor. Just Google it, search up down dizzy on YouTube or whatever. Or when you go out in the quad, make sure you're in a soft place. Like, put your head down. Your head has to be parallel to the ground, and then spin around. Now you have to be committed to it. You only have to go around 3 or 4 times. You're gonna be flat on the ground. You can't not fall down. You'll try it out. Up, down, dizzy. You can search it, or you can try it out in the quad later. Okay, so we're going to make some definitions here. We're going back all through chapter 2 again, where we define position, velocity, acceleration, and then we'll, in the end, come back to our original equations that we had for that. So we've seen all this before. We're just going to put in different variables. By the way, let me go ahead and tell you, before we had x, v, and a. Now we're going to have theta, omega, and alpha. This is omega, not w. It's the lowercase Greek letter omega. And of course, this is alpha. So whereas before x was position, now we're going to have angular position, which is theta. Excuse me. Um, angular velocity, which is omega, and angular acceleration, which is alpha. So when we're defining angular position, we're going to use the angle theta. The SI unit for theta is the radian. Other units include degrees and revolutions. You'll need to be able to translate between those. But first of all, let me define what is, oh, no, never mind. You'll need to know the difference between those. So don't forget this conversion factor that 2 pi radians is equal to 360 degrees, which is equal to 1 revolution. It'll also help you to remember your unit circle. I suspect that a lot of you know it, but this is 0 radians, this is pi over 2 radians, this is pi radians, this is 3 pi over 2 radians, and then this is 2 pi radians. You don't necessarily have to know your unit circle, but you know, it's a good life skill to know your unit circle. All right? And then if I were to put this in degrees or revolutions, or in degrees, this would be 0 degrees, this would be 90 degrees, 180, 270, and 360. And then revolutions, you know, it's 0 revolutions, a quarter, a half, 3/4, 1 full revolution. Also notice this, we'll come back to this, but this is our expression for arc, that S, which is this distance, is equal to the R value times theta. We'll come back to that and how we relate linear quantities to angular quantities. Okay, so angular displacement, we're going to call this delta theta, and it's just equal to theta final minus theta initial. Remember, this is very similar to what we had for displacement before, where we had delta x was x final minus x initial. One difference is that our signs mean something different here. Counterclockwise displacement is going to be positive, and clockwise displacement is negative. One way to remember that is if you know your unit circle, notice that your unit circle moves in a counterclockwise direction, not in a clockwise direction. Another way that you remember it is that clocks then go in the wrong direction. Do you ever get those sort of cheesy science catalogs, like where you can buy geeky things like, I don't know, may the force be with you, stuff like that? Y'all get those catalogs? No, I get them. And in one of them, you can buy this clock. It's like a clock like this, except instead of having the numbers go 12, 1, 2, 3, 4, 5, 6 in the clockwise direction, if you were to look in the clockwise direction, it would go 12, 11, 10, 9. Like all the numbers are switched because it goes, the clock actually travels in the counterclockwise direction instead of the clockwise direction. Because of course the clockwise direction is the negative direction. You don't want your clock moving in the negative direction. You want it moving in the positive direction. Whatever you need to do, remember that. That's fine. But counterclockwise is going to be positive and clockwise will be negative. Now this isn't a direction in the sense that we think of direction, but we'll just think of the sign as being positive or negative in that way. And we'll get back to what the direction of the vector is in a little bit when we get into cross products. Actually, I think we'll get into it a little bit in this chapter. Okay, so angular displacement is positive or negative. Now angular velocity, we're calling this omega, is delta theta over delta t. This is actually our average angular velocity, which is theta final minus theta initial divided by t. And of course, if I want to know my instantaneous, it is the limit as delta t approaches 0 of my average velocity, which is d theta dt. So remember this whole limit thing, this is just the definition of your derivative. All right, and the derivative of the average angular velocity is the instantaneous velocity by definition, because I'm letting that big time interval get really, really small as it goes to 0, delta t goes to 0. So that means that it's the velocity at a particular instant, not over a time interval, but at a particular instant in time. That's what the derivative does for us. And again, if it's clockwise, the sign of the motion is what? Positive or negative? Clockwise is negative, right? And counterclockwise is positive. Let me just make a note here. This is not a direction. The direction will be something different, or we'll talk about, like I said, when we get into cross products. Turns out that the direction is along the axis of rotation. All right. And then we also have angular acceleration. For angular acceleration is our alpha average, just like we had in chapter 2, is delta omega over delta t. And then similarly, the instantaneous is the limit as delta t goes to 0 of that delta omega over delta t. That's d omega dt. All right, which is, of course, the second derivative of theta dt. All right, but the instantaneous acceleration is the, take my average acceleration, let this get really small, then that tells me the acceleration at a particular instant when delta t is really, really small. And again, clockwise is negative, counterclockwise is positive for that angular acceleration. Okay. Now the direction of these angular vectors, um, not terribly important right now, but it will be important when we get into chapter 8, when we get into cross products. But the directions of these angular vectors is given by the right-hand rule. Because if I think about something that's spinning around, you know, it's moving in this direction, we can't really talk about it having a positive or negative direction. Because really, if I think about this thing as it moving around, you know, the direction is never, it's not in this direction, it's not in this direction, it's not in this direction, because it changes with time, right? The direction that this thing is traveling, even if it's moving with a constant angular velocity, it's going to be changing with time. But it turns out that the direction of this is actually given by something we call the right-hand rule, which we'll use a lot in the next chapter, and then we'll use even more next semester when we get into magnetic fields. We're going to use the right-hand rule. We'll let our fingers wrap in the direction of the rotation. and the thumb will give the direction of the vector. It's going to be the fingers of the right hand, actually. Will wrap in the direction of the rotation. There is a left-hand rule where you use your left hand instead, but the right-hand rule, it works because we use a right-handed coordinate system, that looks like this. Um, but we'll let our fingers go in the direction of the rotation, like this, and then our thumb will give the direction of the vector. So if I have an object that's moving with a constant angular velocity like this, the direction of the angular velocity vector will be in which direction? It's going to be coming out at you like one of those 3D movies. So it's going to be coming out of the board. We'll draw that vector, by the way. We'll see this next time. But the angular velocity vector will look like this, and we'll use a symbol that's a circle with a dot in it. It's like an arrow that's coming towards you. You ever had an arrow coming towards you? That's what it would look like a point coming towards you. Whereas if we have an object that is traveling in the opposite direction, what would be the direction of the angular velocity vector for this object? Not down, no. It would be into the page, yeah. So we would say this is into the page. So this is out of the page, and into the page is going to look like an arrow going away from you. What does an arrow going away from you look like? It looks like this. It's like the fletching of the arrow as it goes away from you. So that's the symbol that we use for out of the page, coming towards you, and into the page, going away from you. Not important right now, but it will be important for Chapter 8 when we get there, which will be soon. It'll probably be Monday or Wednesday. But there's no school on Monday, right? I'm not going to be here. Okay? Let's see. I think I have a question here. Oh, okay. So all of our equations are going to work just the same. So remember, with our linear equations, we had this derivation where we started with a equal dv dt and v equals dx dt. So we started with those two definitions, and we derived those two kinematics equations. There were really only two kinematics equations. They were from this, integrating this function, we get v equals v naught. Remember, that's my initial condition. That's my integration constant, that c value, plus a times t. And then we substituted this back in here, and we integrated again, and we got a function for x, which is x naught plus v naught t plus 1/2 a t squared. So these are two kinematics equations. I think I said, but there are some books that will give you a third equation, which is just a substitution of one of these equations into the other. But those are our two kinematics equations. We had a similar definition for our angular quantities, that is alpha equals d omega dt, and omega equals d theta dt. So in a similar way, we can make equations for our angular rotation, and that is that omega equals omega naught plus alpha t, and theta equals theta naught plus omega naught t plus 1/2 alpha t squared. As we did before, this is usually 0, so I'll get rid of that. Similarly, this is usually 0, so we'll get rid of that. I usually won't write that out, but it exists. It's just we're assuming that it's 0. All right, so those are our new kinematics equations. Just want to make it clear, make sure that you're aware that you have an equation sheet now. So make sure that you're up on what's on that. Notice you have those two equations right here, and we have a couple more that we'll get to in this chapter as well. All right, so you will have this on the next test. Just make sure that you're clear on what's on it. Don't be lulled into security with the equation sheet. It's usually not really that much help. I mean, you know these equations anyway because you had it in chapter 2. You're just substituting V for omega, A for alpha, X for theta for X. We can also translate these. So to translate these into their angular. Hold on just a second. Let me see what. Yeah, so we're just letting X equal theta. I said this, but X now becomes theta. V now becomes omega, and A now becomes alpha. So just get familiar with those. It's really just about being familiar with those. It really works exactly the same way. All the stuff that we did before works exactly the same way. We can also translate between angular and linear quantities. So in the previous part, we looked at this. Like if you have a piece of pie that has a certain angle right here, and it has a certain radius, I can find this value, S. S is called the arc, and S is equal to theta times R, um, where theta must be measured in radians in order for this to be true. Because imagine, what if theta extends the full circle? What does this become, the arc equation? The circumference, right? Because if I let S go through the full circle, then theta becomes 2 pi radians, and then 2 pi times r. That's our expression for the circumference of a circle. In a similar way, though, we can say that omega is equal, or excuse me, not omega, v, the speed, the linear speed, is equal to omega times r, and a, I'm going to call this the tangential acceleration, is equal to alpha times r. Uh, Here, omega has to be in radians per second, and here alpha has to be in radians per second squared. These are just magnitudes, because if I imagine that I have an object that's traveling around a circle like this, let's consider its velocity. Say that it's moving with alpha equal to 0. So that means that it's moving around at a constant speed. If I think about the velocity vector is actually constantly changing because the velocity vector is always changing direction. So it has a different acceleration than here. Even though in this case alpha is equal to 0, it actually does have an acceleration. We'll get into that later in the chapter. That's called the centripetal acceleration. But here alpha is just referring to if this object is speeding up as it rotates around. Okay, and then we can translate that to an a. If alpha is not 0, the angular acceleration, then the tangential acceleration also is not 0. Let's try this quick test. Watch your units on this. You have to do a unit transformation to get the answer right. Notice the answers are in radians. Oh shoot, while y'all are doing that, I have to run upstairs, so just take a minute, I'll be right back. see, let's do about 10 more seconds. Just guess if you're not sure. Stop at 250. 250. Oh goodness, let's see. We're all over the board here. So we'll do a couple more practice problems on this. But here I want to go through and I want to pick out what it is that I know. So first thing I want to do, I see that it's at rest. What does that tell me? That's the initial angular velocity. So omega naught is equal to 0. And then I also see that it's moving through 3.2 revolutions. Theta, omega, or alpha, what is that? That's theta. So theta is equal to 3.2 revolutions. And it does that in 2 seconds. So t is 2 seconds before it reaches its final angular speed. I don't know what that is, but I want to know what is its angular acceleration. All right, I know I have these two equations. Omega equals omega naught plus alpha t, and theta equals omega naught t plus 1/2 alpha t squared. Let's see, I know t, I know omega naught. I think it's just alpha that I don't know. Is that right? I don't know alpha. I don't know omega. I don't know alpha. Those are my only unknowns. So it looks like I'm going to be going from here. So I have theta equals omega naught t plus 1/2 alpha t squared. But also remember that I want this in radians per second squared. So I'm going to need to convert this value into radians. I know in 1 revolution, there are how many radians? There are 2 pi. 3.2 times 2 pi. What is that? 18, 19, 20? Just 20.1. We'll just call it 20 radians per second squared. And then I can put in my values. So I say theta equals omega naught t plus 1/2 alpha t squared. Fortunately, omega naught is 0, so this thing goes away. Otherwise, you're solving a quadratic, or you're using the quadratic equation to solve it. And so I have, sorry, this is just radians here, not radians per second squared. You follow me? So now I have 20 radians equals 1/2 alpha, and t is 2 seconds squared. So that's 4, half of that. It's like alpha should be 10. So B is the right answer here. Okay, let's look in the homework. Let's work one of the homework problems for a little bit of extra practice on this. This is a lot like Chapter 2, where we were working 1D kinematics problems. It'll be very, very similar to those. Let's go look at the homework. I'll write that one for y'all. Okay, this is a good one. This one actually, I think, requires a substitution. So here I have a drill bit rotating at 3,600 revolutions per minute, and it rotates through 50 revolutions while coming to rest. So I want to pick out what I know. I have several values here. I have this value, I have this value, and then I also know that it comes to rest. And so I want to figure out what are those values representing. What is the 3,600 revolutions per minute? Is it the initial or the final angular velocity? This is the initial, right? So omega naught equals 3,600 revolutions per minute. 50 revolutions, that's the theta, omega, or alpha. Right, that's my theta. And in my mind, I'm remembering that this is really my theta final. It moves through 50 revolutions, but theta initial was 0. But I'm not going to write that because that's always the case. Most of the time, that's the case. And then it comes to rest, theta omega alpha. That's my omega. It's talking about the speed, and that's equal to 0. This problem's a little bit different from others because often in others, the initial velocity is 0, but in this case, it's not the case. The final velocity is 0. And now I want to know the angular acceleration. That is alpha. When I write down those equations, I can start to think about how we might approach this problem. Let's see. I'm going to label my unknowns. I don't know alpha, and I don't know t. I think those are the only unknowns that I have. I don't know alpha. I don't know t. Um, so I'm going to have to use the quadratic equation to solve, or I'm going to have to substitute one equation into the other. Let's solve this for t, and then we'll substitute it into the other equation. So I say t is equal to omega minus omega naught over alpha. And now I'm going to take this, I'm going to plug it in here, and I'll plug it in here. So I get theta equals omega naught times omega minus omega naught over alpha plus 1/2 alpha times omega minus omega naught over alpha squared. And now I want to solve that for alpha. It looks complicated, but it's not really that complicated because look, I have an alpha squared here and I have an alpha here. So one of these alphas is going to cancel out, leaving me with a common denominator between both of these, which is going to be alpha. You'll see that we're solving alphas are only unknown, and I have a common denominator between this term and this term. So it's actually going to work out pretty simply. I'm going to do that here. Sort of expand that second term. I have theta equals omega naught All right. I'm going to stop there. There's a number of algebra steps here that you need to go through. If you're uncertain about how to go through them, there's a video solution online. But mainly I want to be able to read the problem and be able to pick out what it is that you need to solve for, and then develop a way to approach that, how to solve the kinematics equations for that. All right. Y'all could solve this equation. If you're uncertain, go check it out on the screencast. It is on there how to solve that. But you would need to create the common denominator. It's going to be 2 alpha, and then you'll have theta equals this big thing over 2 alpha. Cross multiply and solve for alpha. Okay, where were we? Let's go back to centripetal forces. Nothing really new here. The only thing new that we have here is that we're relating linear to angular quantities, but really a lot like Chapter 2 up to this point. Now, centripetal acceleration is a little bit different. You know, we talked about if I have something that's moving around with a constant omega, that means that it rotates around at a speed, at an angular speed that's constant, so many revolutions per second. And you can have that or you can have it accelerating. But if I have this moving around at a constant speed, then it has a velocity at each instant. So if I think about this ball when it comes over here, it has a velocity vector as it goes around At this instant, the velocity vector is away from you, a linear velocity vector that's pointing away from you. But over here, that velocity vector is going to be to your what? Your left or your right? Am I right? You're left, right? So, yeah, as it goes around like this, the velocity vector is changing all the time, right? Out here, it's in that direction. Over here, it's towards the board. Behind me, it's over in that direction. It's constantly changing. So the velocity vector, as I go around this circle, is always going to be tangent to the circle. The velocity vector is always changing. So even though it's moving at a constant speed, the velocity, which remember is a vector, is always changing. That's kind of a funky thing that we don't really think about, but even though it might constantly have a speed that's, say, 2 meters per second, the velocity of this object is always changing. And if we have a changing velocity, that means we have to have a what? It has to be accelerating. So there is a force that's causing an acceleration, and in this case, that acceleration is changing not the magnitude of the velocity, but it's changing the direction of the velocity, right? So this centripetal acceleration, we call it, is working to change the direction. The centripetal acceleration describes how the velocity changes direction. It's still going to have the same units, meters per second squared, but it's instead of describing how the velocity changes magnitude, it's now going to describe how the velocity changes direction. Um, we're going to call this centripetal acceleration AC, and it has a value equal to the speed squared divided by the radius of the path. The radius of the path is just the distance from here to here, um, and v is just the speed, the constant linear speed. Sometimes, by the way, you might see this not as AC, but as AR. It's called that because R stands for radial, because the centripetal acceleration always acts radially. The centripetal acceleration is always in that direction. So a lot of people will call it A sub R because R stands for radial. The centripetal acceleration is always radial. That's what centripetal means, actually. It means center seeking, always towards the center. So our centripetal acceleration will always be towards the center of the circle. That's in contrast to that Faith Hill song. You know that Faith Hill song? Isn't it Faith Hill? Where she talks about centrifugal forces or centrifugal motion. You know that song? It's centrifugal motion. You know, what is that song called? It is Faith Hill, right? This Kiss, yes. This Kiss, this Kiss. Is that Faith Hill? You know where she's from? She's from Mississippi. Do you know where I'm from? There are a lot of famous people from Mississippi. There really are. Who is that? Oh yeah, right, right. Um, no, there really are a lot of famous people from Mississippi. I'm not playing up Mississippi, but like William Faulkner's from there. That other famous writer, the Catholic writer, what's her name? That lady. I forget her name right now. A lot of famous people from Mississippi. All right. Anyway, so it's center seeking. Centripetal means center seeking. We can have an alternate form of this. Looks like this. If I substitute that V equals omega R, if AC is equal to V squared over R, I can substitute this in omega r squared over r. I'll just get an alternate form, and that is that the centripetal acceleration is equal to omega squared r. See, because one of these r's cancels, and I'm just left with omega squared r. So you can either have AC equals v squared over r if you know the actual linear speed, r omega squared r. Sometimes you don't know the linear speed, you just know the angular speed. You could find it, of course, right, because linear speed is just omega and what? If I have the angular speed and I want to find the linear speed, what do? I'll just do this, right? If I know omega, I multiply it times r to get the linear speed. But sometimes it's better to think about it in this way, that the centripetal acceleration is omega squared r. Okay, so if we have an acceleration, that means we have a force, right? And a force is a centripetal force. This always confused me because I never really understood what the centripetal force was. And then it dawned upon me that the centripetal force is not really a separate force. It's really just sort of a name that we give to a force that already exists. So the centripetal force is the force that causes circular motion. And that can be different in every scenario. So for example, what is the centripetal force in this case? The tension in the string. So the tension in the string here is causing the circular motion. But it can have different things as well. What about if you're in your car and you're going around a curve? What is the force that keeps your car in that circular path, that you don't run off into the cane fields in a straight line path? The frictional force between the tires and the road. So in that case, there's no string holding you on the road. In that case, it's the frictional force is the centripetal force. Or have you ever been on one of those rides at the fair where you stand up against the wall and it spins around? You've been on, and then you rise up off the ground? It's pretty cool, right? What's the centripetal force in that case? It's not a tension, it's not a friction. What is it? It's the normal force. Yeah, it's not the gravitational force. That's what most people think. The gravitational force is acting down. It's not acting towards the center of the circle, but it's the normal force because you feel that wall is pushing up against you. It's pushing you into that circular path. If the wall was to disappear, you'd just fly off in a straight line and go over to the waffle stand or whatever. Okay? So it's the normal force that causes you to move in a circular path. So like with the hand and the ball and the string, the centripetal force is called by the tension. So it is this force that causes the ball to change the direction. So the tension is the centripetal force. So we'll encounter some problems where we have to figure out, well, we'll be talking about the centripetal force, and so we'll have to figure out what is the centripetal force in this particular case. And it's not going to be that the centripetal force is a separate force. It's going to be that one of the forces involved in the problem will be the centripetal force. Uh, let's see. So we can calculate the centripetal force. It's the centripetal force, or F equals ma in general. Uh, And for our centripetal force, it's just going to be the mass times the centripetal acceleration, which is going to be mv squared over r. So this is our centripetal force. So if I have, the car on the roadway, where our frictional force is acting on the car, in this case, the centripetal force is the frictional force. Or if I have the ball on the string, where the tension in the string is causing a centripetal force or a circular motion. In this case, the tension is the centripetal force. Or like on the, what do they call it? It's like the vomit comet or something. Is that what they call those rides? I don't know. Anyway, if you're on one of those rides and you have all the people that are there, you have the normal force that's causing them to go in a circular path. In that case, the normal force is the centripetal force. All of those act as a centripetal force because they cause you to go into circular motion. And in each of those cases, you can say that those forces, the frictional force, the tension, or the normal force, depending on the scenario, that those are equal to mv squared over r. All right, so like for example, on those rides, you can calculate the normal force that acts upon you if you know your linear speed and the radius of the ride. Well, so what happens if you take that force away? Let's try this. We will wrap up with this. So if I have an object that's moving in a circular path, like this ball, and I can take away the centripetal force, what happens to the object? If I take away the centripetal force, what happens to the object? Will it follow a path that continues in a circular motion at point A? Will it go out in a straight line? Will it sort of fly off away from the circular path? Or will it fly straight out? So if in some way I was able to remove the string, which would remove the centripetal force completely, what would happen to the ball? Would it follow paths A, B, or C? Go ahead and click in A, B, or C. You can think Newton's first law in this as well. This is a good application of Newton's first law, that if there are no forces acting on an object, which would be the case if I take away the string, uh, the object will continue in its current state of motion. And so you want to think about, if I'm spinning this thing, when I release the string, what is its state of motion? I'm going to stop this a few more seconds. So let's see. So I'm going to try to release this right about here. So it's going to come sort of towards you. Y'all watch out. I'm not real good at releasing it at exactly the right point, so it could go anywhere. All right, but I'm going to try to release it right here, and then you can see where it goes. Let's get it a little faster. Whoop. Yeah. All right. I released it sort of there, and it followed this straight line path over towards Ainsley. All right, so most of you got this right, but B is the right answer. And again, a good application of Newton's first law, that Newton's first law says if I don't have any forces, it's going to continue in its current state of motion. So at this point, the velocity is in this direction. That's the direction of a velocity vector. If I take away the force, then it's going to continue in that direction because of Newton's second law, because that's what it wants to do, that it wants to continue in its current state of motion. All right, folks,